All right, welcome back. So, this is the Fundamental Theorem of Calculus, day 2. Okay, and there are technically 2 parts to the Fundamental Theorem of Calculus. The first part of the Fundamental Theorem of Calculus is the fact that, again, the idea that the derivatives and antiderivatives, derivatives and integrals, are really kind of inverse processes of the other, right? Like just like squaring and square rooting, just like multiplying and dividing, just like adding and subtracting. They're inverse properties of inverse operations, basically, right? And you can say that if you take the derivative of the integral, it gets you back the original, or it gets you back the antiderivative, right? Like the g prime is gonna cancel that stuff out. G prime is technically equal to f of x in there. And remember those problems that we did yesterday, where if you have something up here in the integral, you're going to take that and put that in there, right? You're basically going to substitute it in, and then it becomes that new function. So g prime of x was square root of 1 plus x squared. The only thing you have to watch out for is that when there's a whole brand new function up top there, then when you put it in, you're going to have to apply the chain rule, take the derivative of that as well, which we did there. And then we talked about Fundamental Theorem of Calculus Part 2, which again, I kind of already gave away. I kind of let the cat out of the bag a little early. Like I said, I think about how I want to teach this next year. I might like combine these 2 sections because we don't really use the limit thing a lot. That we did that one problem that we never actually applied because it's way too cumbersome. But the Fundamental Theorem of Calculus Part 2 basically says that you can take the antiderivative and you take f of b minus f of a, find the difference between the 2, and that will give you the true area underneath the curve from a to b, right? The antiderivative will give you the area underneath the curve. All right, so let's take a look here. Find the area underneath the parabola of y equals x squared from 0 to 1. You know, it's interesting. This problem is the one that took us like 30 minutes on that first day we learned integrals. Right? That first, section 5.1, that first day we did integrals, we did all those rectangles. We were looking at this exact problem. Right? But now we could do this within seconds. We're going to write it from 0 to 1 of x squared dx, which is technically the antiderivative. Now, what's the antiderivative of x squared? X to the third over 3, right? Bump up the power and divide from 1 to 0, right? Excuse me. Okay, so that is 1 to the third over 3 minus 0 to the third over 3. Well, 1 to the third is 1. And this all goes to 0, so that's just 1/3. Remember how long that took us? Right? Using the antiderivative is so much more cleaner, so much easier, yes, right? Than using any sort of Riemann sum. Because again, the Riemann sum just approximates it anyway, right? That's just an approximation. Imagine, like, I'm still going to geek out about like the history of this. Like, imagine being the guy that's like, wait a sec. If you take the antiderivative, is that equal to the area? That's so cool. All right. Evaluate the integral from 3 to 6 of dx over x. This looks weird. Dx over x. You know, we normally don't see dx like with the function. So what do we do here? Well, let's just, if it's with the function, and we don't normally see it with the function, let's just remove it from the function, right? If I wanted this to look like this with something dx, right? What should go here if I take out the dx? 1 over x, right? Because it was dx over x, so 1 over x. Okay, what is the antiderivative of 1 over x? ln of x. Good, that's that weird one, right? Be careful, because you might try to think of it as, I'm going to put this in red because it's wrong. You might try to think of it as this, right? But if I go to bump up the power, what's the power going to be? X to the 0, And things go haywire from there, right? And it's like, well, x of 0 is 1. It would be 1 over, yeah, no. Don't do that. It's ln. Right? So it's ln of x from 3 to 6. Which basically means top minus bottom, ln of 6 minus ln of 3. Let's evaluate that. ln of 6 minus ln of 3. And that gives me 0.69. 0.69. And remember, please don't lose sight of the end goal of this thing. Like, what is that notation actually telling you? Well, that's looking at this thing, 1 over x, where? From 3 to 6. That is 0.69. Does that make sense? Never lose sight of the end goal that this is the process of finding the area underneath the curve. Right? It's just a algebraic way to do it. Find the area under the cosine curve from 0 to b, where b is between 0 and pi over 2. So this is basically just telling you to generalize it. Generalize it. What if I don't tell you where b is? What if I just say, find the area under the cosine curve from 0 to b, where b is somewhere between 0 and pi over 2. Where's pi over 2? Where's that at? At least you're honest. Right? She said no idea. Where is pi over 2? What angle is that? 90, right? That's 90. So if b is between 0 and 90, what does that tell me about the area underneath the curve? Right? Thinking about it graphically, cosine starts at the top, right? And it goes like this. I don't need to keep it going because where's this going to stop? There, right? If I know this is 0 to pi over 2, okay, and I put b somewhere along the way in here, what's the area underneath the curve from 0 to b? That's what I'm looking at here. And you may be thinking, well, how do we calculate that if it's unknown? If we just say 0 to b? I don't know. Let's figure it out. From 0 to b of cosine of x dx. Well, we know, find the antiderivative. What is the antiderivative of cosine? Now, you might need to think this one through because the negatives are always tricky, right? The negatives are always tricky. What is the derivative of sine? The derivative of sine is just cosine, right? Derivative of sine is cosine. So what's the antiderivative of cosine? Positive sine, right? The antiderivative of cosine is positive sine. The derivative of sine is cosine, so the antiderivative of cosine is positive sine. Right? Be careful with that. I always have to like write it out this way because I know the derivatives, but the antiderivatives can get a little tricky. Be careful. The derivative of cosine is negative sine. Right? The derivative of cosine is negative sine, but I'm not talking about derivative. I'm talking about antiderivative. What if I end with cosine? What do I start with? I start with sine. Okay, so we have sine x. Excuse me, sine x from 0 to b. Life is so nice when you start at 0. You're going to find that problems that start at 0 tend to be a little easier because when you plug them in, it's usually 0. Let's see. Sine b minus sine 0. What is sine at 0? What's the y value at angle 0? 0. Right. So this actually turns out to be sine b. And that's fully reduced, right? So it's interesting to point out that if you want to calculate the area underneath the curve at any given point from 0 to pi over 2 on cosine, all you have to do is run that same value through sine. Right? You want to find the area underneath the curve from 0 to pi over 4. just find sine of pi over 4. You want to find the area underneath the curve of cosine from 0 to pi over 3, just run sine of pi over 3. And that tells you the area underneath the curve at that point. Okay. So sometimes, be prepared, sometimes you're not going to get just a number, a concrete number. Sometimes you will get another function back out again that you can evaluate then, right, at any given moment after that. Is this the last one? This is the last one, yeah. There are two reasons why I want to, one, I think this is kind of a cool problem. What's wrong with this? But the second thing that I want to show, second reason I wanted to show you this is because sometimes the notation, I'm going to highlight it here, sometimes the notation looks like that. Like you might see books that looks like a bracket instead of just a vertical line. I mean, it's just whatever the person writing it does there. So you might see brackets in that way as well. All right. So if I'm saying what's wrong with this calculation, it might be a good idea to just write it out and see what's going on with it. Try to go from the beginning. So the first thing I should do is write it as a polynomial, get that x squared out of the denominator from -1 to 3 of x to the -2nd dx. Okay. What's the antiderivative of x to the -2nd? Bump up the power. -2 goes to -1, and then we divide by -1. So x to the -1st over -1 from -1 to 3. Are we good with our calculation so far, looking back up at the top? Okay, so they didn't screw up yet. I mean, it's interesting to say that what is wrong, because there's obviously something wrong. All right. Well, that would be, bring the negative out, 1 over x, -1 over x, from -1 to 3. And then here, let's plug in top minus bottom, -1 over, oops. Yeah, that's right. I got it. I'm writing it right. Because the negative has to stay even when I plug in the -1. It will eventually cancel here. But it's -1 over 3 minus -1 over -1. All right, so those will cancel here. -1/3, those cancel, -1. Okay, well, -1/3 minus 1. What is -1/3 minus 1? So what's wrong with that? I mean, like the question implies, something is wrong. What is wrong? I know. Do you know? What is wrong? It's not necessarily, this word calculation is kind of, might be throwing you off a little bit. It might lead you in the wrong direction where, like, to think that something is wrong with the algebra. Nothing is wrong with the algebra of this. Nothing is wrong with the computation of this. Think about 1 over x squared. Think about 1 over x squared. What is this truly representing? Again, don't lose sight of the end goal. What is that truly representing? The area under the curve of that, right? Well, what does that look like then? Well, I'll just write it as x to the negative second. Excuse me, man. X to the negative second. Oh, come on now. Zoom 6. So I'm finding the area underneath the curve from, let's change our window up a little bit, from -1 to 3. So let's look at it from -2 to +4. Is that area truly -4/3? Why is it getting thrown off like that? Why is it getting thrown off like that? Why am I actually computing to be a number? What should the area be? The area is actually infinite, isn't it? Why? Because there is a horizontal asymptote. Where? At 0. So why doesn't the fundamental theorem of calculus work? Like, why is this not working? Well, because we may have forgotten one of the basic premises of the fundamental theorem of calculus. It's got to be continuous along that interval. If it is not continuous, then the fundamental theorem of calculus doesn't even hold. Okay? It has to be continuous. There has to be continuity from A to B. Where you're looking at, from A to B, there's got to be continuity. If there's not continuity, it's not like you're going to get an error when you go to calculate the fundamental theorem of calculus. So be careful with that. Like, you might be going along, plugging and chugging, and then you're like, oh, I get a number, there's my answer, boom, done. But unfortunately, you may have missed right at the very beginning, does the fundamental theorem of calculus actually work on this? Well, you got to see if it's continuous and differentiable, right? It's got to be continuous and differentiable. Can't be any, and think about the restrictions on that. There's, there's jump discontinuities, there's infinite discontinuities, there's removable discontinuities, and it's got to be differentiable everywhere as well, right? There's no corner points, no vertical tangents, those types of things. Okay. All right. I think this is just kind of like a summarization of the fundamental theorem of calculus. So I talk a lot about, like, and even in the questions, I printed out the review for the quiz as well. And even in the questions for the review, you'll have to know the difference between FTC1 and FTC2. I call this FTC1, obviously, FTC1, and this FTC2, okay? FTC1 basically just says that the derivative of the integral is get you the original, right? So get you that function inside there. That's the more you like substitute it in and whatnot. FTC2 is our f of b, or sorry, f of x, a to b, right? That's our top minus bottom thing. Okay. All right, that is it for the notes for section 5.3. Let me stop the video.